There are no limits to imagination, they say. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. Consider an apple falling from a tree. What presses or draws the apple downwards? Gravity, you say. Well, imagine gravity then. There are many ways to think about gravity. For example, one may consider space itself to be a kind of fabric which is fastened to some structure, such that a body of mass lying on top of it will distort it. Alternatively, what drives gravity may be a particle racing back and forth between the apple and the earth to inform both that they should attract each other. Physics is about facts, isn't it? Many people think exactly that because both ways of explaining gravity have been used so often that it is easy to believe them to be truth instead of describing truth, which in fact they don't actually do very well. For example, think only about how we live in a three-dimensional world, while our piece of fabric is two-dimensional. Thus, we get lost between what we think we know and what we imagine. For it is possible to come up with solutions to all sorts of questions. Imagination is almost without limits after all. Does that mean we should just invent things? Einstein's equations on general relativity, for instance, predict something called gravitational lensing. If there is, say, a galaxy in the way of the light from another galaxy behind it, then there will be smudges of light around the galaxy in the foreground. Depending on the mass distribution of that foreground galaxy, those smudges can be points, banana shapes, yes, banana shapes, or even rings. Now, you may be listening to this piece, not watching it. So you'll just have to believe me that taking up an image, say of the Einstein cross or any other suitable object in the deep sky, makes it quite simple to describe the effect. The foreground galaxy simply bends light around itself. However, we don't just want to describe, do we? We would like to know why things look like they do. We want to know how they work. How can a galaxy bend light around itself? I mean, huh? Consider now a bright kid who thinks a little bit more about the Einstein cross and concludes that this has to be the same phenomenon as when you are up to your knees in water and your legs look like they are folded forward. The kid is both interested and shows deductive skills, but fails to grasp the truth by quite some margin. What will you answer as a parent or a teacher or as that random guy in the street who can't believe that a kid would come up to him and ask such a question? Perhaps you start talking about fabrics with weights in them. You know, like the gravitational wells at your local science center. For in this way, one has to imagine gravitational lensing. Light follows a straight line which starts at its source and follows the curvature of our fabric around the foreground. No, let's stop. We have already established that this is not an explanation. Let us rather admit that we should probably not be so surprised about physics being so alien to many people. Curiosity isn't lacking, but it is challenging to get a hold of, since physics deals with things that seem to have no deep, satisfactory explanation. And what is worse, the thoughts I've just uttered don't apply only to gravity. They apply to quantum physics, aerodynamics, the Big Bang, whatever that is, and the particle wave duality. With respect to these and many, many other topics like them, it is simply necessary for us to invent something that resembles an explanation. We do so happily, and the more we use the images we think up, the more we tend to accept them as reality. Don't deny it, but try to pay attention to what you say and do in everyday life. We are humans. Humans do things like this all the time. Back to gravity. And for some reason, my daughter. When she was around 1 year old, her favorite game was to drop stuff. Her eyes eagerly followed every Lego giraffe, teddy bear or porridge plate, which she pushed over the side of the table. Then she would smile at me. I usually sat on the floor already, prepared as I was. Did she know what gravity is? That is a weird question in many ways. It has a rather obvious answer too. Then consider this. Do you know what gravity is? Of course you do. And that is weird, isn't it? Why do you know what gravity is while my daughter didn't? How can you know it? How can we know what gravity is? We know it because it is part of us. We humans have developed into what we are now over millions of years. Gravity has been with us the whole time. We have raised ourselves upright and become bipedal despite gravity. No, I shouldn't say despite. Without gravity, we wouldn't exist, but that is a different story altogether. Gravity is part of what defines us as humans. Now, even though a grown-up person has some sort of understanding for what gravity is, we will still have to assume that every child grows through his or her own experiences. And to be frank, that process doesn't seem to be too boring either. My daughter, at any rate, laughs heartily when Daddy puts the Lego giraffe back onto the table in front of her. It will be down on the floor again after about 2 seconds. She knows that. There have been many experiments. I know that too. There have been many experiments. And that is just the way of science too, really. One examines and investigates. If the same thing happens often enough, one begins to become more confident about having learned something. So science as a process is not foreign to us. I may even go a step further and state that actually we seem to be born scientists. Children come out of their mothers and begin almost at once to try to find out about things, don't they? Fortunately, some of us manage to stay scientists all our lives. No, this is not meant to be sarcastic at all, for where would we be without those who keep their curiosity throughout their lives, despite life not always rewarding them for their curiosity? What would we do without the Teslas and the Da Vincis of this world? There are innumerable ways for curiosity to manifest itself. The world is filled to the brim with enthusiastic biologists, painters, geologists, architects, and many others. What I want to focus on here, however, is astronomy, since it is the science which, at least traditionally, concerns the universe itself. Astronomy may very well be the oldest of all the disciplines of science. In the beginning, however, the skies and what could be seen there were examined under a premise which is rather different from what we understand to be science today. Don't misunderstand me now. The movements of the sun, the fixed stars, and the quote-unquote wandering stars like Jupiter, Saturn, Mars, and even the rarely appearing Mercury were known already to the Egyptians and other cultures 6,000 years ago. Archaeologists found what is most likely a star map in the tomb of Ramses VI. Yet, and this may not be all that surprising, the movements of the objects in the sky were correlated with stories which guided people in their daily lives. It was all about the blessing of a deity. Perhaps it was also a little bit about power, getting it or keeping it. For example, it was said that the pharaohs had to help the sun god Ra in his underworld fights against the basilisk every night. Without the pharaoh, the sun wouldn't rise the next morning. What a useful thing to take credit for. Then there were the Greeks. The Hellenic culture, which spread over big parts of the Mediterranean for a while, took religion less and less seriously with time. People slowly gained knowledge of what we summarize as geometry today. The measurements of distance was formalized, trigonometry was invented, or should we rather say discovered, so that ideas could be correlated to one another as long as it was possible to express them in terms of geometry. This led to discussions of ideas, which themselves could no longer be heralded by a priest with secret knowledge. A good example for this is Claudius Ptolemaios of Alexandria, Ptolemy for short. His scientific endeavors are amongst the most interesting, in that no one has ever been remembered as selectively as he is. parts of his work survived about 1400 years in the form of dogma. Ptolemy conducted his first experiments in the year 127 and his last in 151. During that time there was no developed theory of how bodies moved under the influence of forces, which we call mechanics today. Philosophers very often had to come to their own conclusions with respect to the simplest things, or the most difficult things, if one wants to look at it that way. The amazingly accurate answer to life, the universe and everything was therefore a matter of opinion, and discussed with rather more gusto. The movement of the bodies in the sky turned out to be especially challenging. What does one in fact do without knowledge of mechanics here? One thinks beauty, simple as that. What is beautiful has to be true. Ptolemy thought this to be the case, and many others did too. It simply had to be possible to explain the movement of the heavenly bodies with the help of perfect geometrical shapes, such as circles and spheres, whatever it was that made a circle or sphere perfect to a Hellenic philosopher. Ptolemy actually managed to do this. He found a way to explain all movement in the sky as he knew it, with the help of circles and spheres. But let us start, as it were, at the beginning. The first observation Ptolemy made was that Earth had to be a sphere. Why? He noticed the same things we know and see today, that is, the horizon and how objects close to it behave, as well as the change in the star map as one moves in north-south direction. Yes, to us pictures of the Earth taken by astronauts and space probes do help a little too, but these pictures are not necessary to draw a conclusion here. It is worth noting too that the spherical Earth is something people did not believe in for 1400 years afterwards. The next problem then became how such a sphere would be fastened in space. What was it fastened to? Ptolemy's answer was rather ingenious. No matter where one went, things always fell down. If Earth was a sphere, that meant that everything fell towards a common center, inwards, if you will. But if that was the case, then why would Earth have to be fastened to anything at all? If a bit of Earth were ripped out, the only thing it would do is fall back. He concluded, on the basis of experiments and observation, that Earth hovered freely in space, with sky on all sides around it. Let the gravity, yes, that pun is intended, of this conclusion in the 2nd century sink in before we continue. Ptolemy observed the stars as well. What he saw led him to believe that they were fixed to the inside of another sphere, and that the Earth was the center of this other sphere. But since he had also found out that the stars shone with the same intensity at different places on Earth, he concluded that Earth's dimensions had to be minuscule when compared to those of the heavenly sphere. Now, realizing that Ptolemy came as far as this in his conclusions, the next step seems at first to be rather surprising. He concluded that it had to be the heavenly sphere which rotated, not the Earth. Think about this yourselves for a moment. Which is more likely to be the one rotating, the Earth or the immense heavenly sphere? What does physics, or indeed common sense, say about these distant stars as they rotate once per day around 360 degrees? The stars are very, very fast, that is what it says. Much too fast, in fact. As far as we understand, Ptolemy knew about this rather well too. It is possible to start asking then why he stood by a non-rotating Earth, even convincing others of his idea. It is said that he could not find a satisfactory answer to the question as to why the air would rotate with the planet. He thought it couldn't. Don't ask why. It's a mystery, of sorts, at least to me. On to the sun, the moon, and the planets. Sun and moon were rather easy to explain. They moved in circles around the Earth. The planets, however, were a different story. They seemed, at times, to move backwards. It is quite an achievement of Ptolemy's that he managed to explain this motion with the help of circles. I mean, he postulated that the planets moved in epicycles, that is, described circular movements on top of a circular movement. Perfect, beautiful epicycles, the way it was supposed to be. What is beautiful had to be true. But does it help to understand? It took around 1400 years before circles had to give way as forms with which to describe planetary motion. But when this first happened, other beautiful ideas had to be dropped too. Speaking of Ptolemy, one of the hidden wonders of history is that rather consciously selected parts of his teachings survived for around 1400 years as doctrines. As we continue now, we will not stay to talk about the contributions of Arabic, Indian, and Chinese astronomers, who sometimes disproved, sometimes confirmed, and further developed the knowledge of the Hellenic philosophers. We will also walk past those few scattered monks and Christian philosophers who tried to adjust the old knowledge to the dogma of the Church. We can't forget all these valuable contributions, of course, but for the purposes of this particular story, it is most effective to discuss at once one Nicolaus Copernicus. Copernicus was not the first to conclude that the Earth could not be the center of the universe. Amongst others, Pythagoras, he of the triangles, most likely came to this conclusion too, albeit in a somewhat, interesting manner. Check it for yourself, it's worth it. Copernicus couldn't see how Ptolemy's argument against the rotation of Earth was true. There were additional questions. If there was a heavenly sphere, what was it made of? What would the outside of that sphere have looked like? Perhaps the outside of the sphere was the abode of God. What pious Copernicus thought when his mind took him to pondering the heavens isn't known. It is undisputed, however, that to him there had to be a different solution. The Earth could hardly be the center of everything. The problem then became how the Earth could be stationary if it wasn't the center everything fell towards. Or was it stationary at all? To Copernicus it came rather naturally to assume that the Earth could move, and if the Earth did that, the question of how everything moved in relation to each other had to be answered anew. But how? Start with the idea of relativity. Something that doesn't move looks as if it moves backwards to somebody who does move. Copernicus read and pondered and examined observational results and arrived in the end at his version of what we now call the heliocentric model. And you know what that was? A collection of perfect circles. That's what it was. Copernicus was, after all, a pious man. Next up was Tycho de Bry, a 17-year-old from Denmark, who noticed that the position of the wandering stars did not quite agree with the day's theories about where they should be. He started long-term observations of planetary movement. The result of this work was data accumulated over 20 years, all that without a telescope too. These were, in fact, 20 years of data which young Johannes Kepler received at Tycho's deathbed. What Kepler saw in Tycho's data was that the planets did not move in circles and not at all in epicycles. The only way to explain Tycho's data was to assume that the planets moved in elliptic orbits with the Sun in one of the focal points of the ellipse. But wait, we know today that the planets move in orbits which are almost circles. So was it really possible for Tycho to observe that accurately without the help of telescopes, to recognize these tiny elongations in the planet's orbits? Well, yes, at least in the case of Mars, which has a slightly more elongated orbit than the other planets. And thankfully, Mars had become one of the focal points, as it were, of observation for Tycho. A snap of the fingers later, and gone were the circles. After Kepler, or maybe with Kepler, mathematics was introduced into the equation. Research was still all about the movements of the planets, but the calculations became more and more complex with time. In fact, they became so complex that the next scientist in our series had to invent his own way of computing things. Of course, we talk about calculus and the man with or without the needle in his eye socket, Sir Isaac Newton. By the way, Newton was not the only one during this time who developed calculus. Gottfried Leibniz did the same in Germany. Today we use Leibniz's notation, while Newton used the newly found mathematics to a much greater degree than the German mathematician. Anyway, Newton thought that if an object is picked up from the ground and then let go, it will increase its speed on the way down. If one lets it go from a greater height, it will be faster when it hits the ground. And that is not a surprise at all. My daughter has in fact come as far as that too. But Newton noticed two things here. Firstly, it was rather natural to assume that whatever drew the object to the ground became weaker at greater height. Secondly, it seemed as if there was no obvious boundary height at which that force would stop to exist. It would have to become weaker with distance, but would never completely disappear. This meant, amongst other things, that the moon had to feel it too. Yet the moon doesn't fall down. With the help of the mathematical tools he himself was so instrumental in developing, Newton found out that it would fall down if it ever stopped moving laterally. The object which is at rest before it is let go will fall down, while the moon is not at rest and does not. In other words, the vertical force at work on the object or the moon not only could be but had to be the same. We call this force gravity. After this, the rest became rather apparent. If the moon was held in place in orbit around Earth by gravity, then gravity had to be responsible for the orbits of the planets around the Sun too. Newton could derive Kepler's laws mathematically and ended up doing nothing less than presenting to the world the first scientific and all-inclusive theory for life, the universe and everything. The universe, anyway. And this was a universe which could be described by mathematical formulas. A universe which could be described by physics. This is Newton's mechanics. Do you know the feeling? That is the feeling of working on something so hard as to exhaust yourself and finally having it all come together in some few symbols and letters, expressing physical quantities. F equals m times a. There is satisfaction in that. It is a sort of mathematical catharsis. It is like the first cup of coffee in the new house which one has built with one's own two hands. It is, in one word, beautiful. How Newton would have reacted to being confronted with thoughts like this is anybody's guess. All indications point towards these kind of considerations being somewhat foreign to him. The truth is that very few scientists during Newton's time even had the chance to experience something similar to mathematical catharsis. Just take Galileo Galilei. Galileo had to defend his life and his science in a much more direct manner than many of the others for saying that the heavens weren't perfect. He used his telescope to show that the sun had spots, that there were craters on the moon and many other things like this. He simply showed that the objects in the sky weren't perfect or beautiful, as the church claimed they should be. But then tell me that the sun, with its intertwining flows of radiating plasma and its spots which may or may not explode into the solar system, isn't beautiful. You can't say that without lying, right? Perhaps, only perhaps, what is beautiful doesn't have to be true, but what is true is beautiful. Isaac Newton formulated a theory for all of the universe known at the time, yet that was only part of his scientific work. Before he even spent one thought on mechanics, Newton laid the foundation of what is the most important observational tool of exploring the much greater known universe of today. There is no hyperbole in that paragraph. Young Newton was rather observant of his surroundings. To take an example, he wondered about where the colors of the rainbow would come from. In order to find out, he constructed experiments, one of which showed what happened. When a ray of light from the sun is isolated through a hole in the wall, then this ray can be led into a prism where the colors are separated, and the ray as a whole is taken off its original path as well. The men of the church didn't protest. They probably should have, since this experiment showed that even the heavenly light itself was not perfect. But then, of course, a rainbow is undoubtedly beautiful, and the knowledge of how it comes about does not need to subtract anything from the experience. In fact, one may argue that knowledge only adds to the fascination. At any rate, being able to split light into its colors made it possible to examine the nature of its source, and the nature of what lay in between the source and the observer. The concept one needs to understand this is that of the wavelength and some quantum physics. The shorter the wavelength, the more energy the light has. Violet light, for example, has more energy than red light, since its wavelength is smaller. By the way, did you know that we cannot actually see all the colors of the spectrum the sun sends out, but only those at wavelengths from roughly 400 to 700 nanometers? When thinking of the sun's spectrum of colors, which is vast compared to what our eyes pick up, one could imagine that a plot of it would have to be a nice and smooth line, running from lower to higher wavelengths. Perhaps you know enough physics to know the shape of that line too, the so-called black body spectrum. The actual spectrum of sunlight isn't like that though. Well, it's close, but not quite. It looks rather more like something is missing at some places. These bite-outs we call absorption lines, which in this case are due to the Earth's atmosphere between us and the Sun. How? An atom or molecule has different energy levels, which restricts the atom to only absorb or send out light of a particular wavelength. The molecules and atoms in the air all have such energy levels and absorb light of different wavelengths to different degrees. Turning the argument around, this means that light of a particular wavelength can be correlated to a particular chemical element. The light's intensity then gives us information on how much of this element is present in the light source. And by building instruments which can see wavelengths our eyes cannot, the opportunities and possibilities for observation became enormous. One can, for example, find out that there is a lot of hydrogen in the universe and why that is the case. One can find out about the structure of the universe around us and about how the Sun belongs to a galaxy of around 400 billion stars, such that on the whole, it is not really all that special in the cosmic perspective. Another thing entirely is that everything in the universe seems to be moving away from us. Truth be told, it may seem to the observer that the universe itself is expanding. This means that everything was very close to each other once. We think that at one point there was nothing, which exploded. That is a Pratchett quote, and also a rather big conclusion, and perhaps it's not self-evident anymore where this conclusion is drawn from. What we have to talk about here are mathematical models, that is, solutions to sets of equations, in particular to the Einstein field equations. The variables in these equations can be the time or the average distance of objects in the universe to each other, or a host of other things. And the solutions to the equations give us information about how these variables develop with respect to each other. There is a problem, however. Einstein's system of equations is so complex that the solutions give information only under a certain set of conditions. At the time the universe began, for example, our solutions are infinite. They don't work. To repeat, we have models, equations that is, which describe the beginning and progression of the universe to whatever fate it may have. Yet we have no way of interpreting these equations as a whole. Still, we think that in the beginning there was nothing which exploded. We expressed this rather directly. We have even given it a by now famous name, the Big Bang. The Big Bang theory is not the only example of this either. In the same system of equations by Einstein, one can also find black holes. These have inspired human imagination about as far as anything, with their own Hollywood movies, countless novels and comic book stories, as well as the odd kid choosing astrophysics as a profession in order to find out about them. Big Bang and black holes are inventions, virtually empty expressions, which are used to conjure a kind of description of the physical phenomena in question. There is nothing explosive about the Big Bang. That doesn't mean that the researchers are wrong, or worse, that they can be charged with a scientist's equivalent to heterodoxy. The scientists who communicate this knowledge know what they are talking about, so when the cameras are turned off, the words change. There are less explosions out of nothing, and more approximation limits, models and singularities. There are many mathematical approximation techniques, some of which bear strange names like perturbation theory, which make it possible to examine what happens when our models break down. The only things that are needed are a little experience in mathematics, the knowledge that we deal in approximations and not truths, and enough time to work intensively with the equations over an extended period of time. When we have gained enough experience, we begin to understand. This is just as true for my daughter learning about gravitation as it is for, say, the medieval church builder or, Brian Cox finding a good way to present the physics behind black holes on TV. There is no principal difference for any of these three examples. Learning about physics itself is like this too. It is about finding mathematical equations and then using them often enough, while ever changing the conditions applied to them. It is about learning what the equations can, and perhaps more importantly what they cannot describe. Then understanding will, at the end, arise more or less by itself. Remember how this tale began, and how it developed. The way the world's thinkers approached the biggest problems never stopped changing. First, there was the mythical approach. which got softened and slightly changed by the advent of geometry and its reliance on the truth behind beauty, all the way to mathematical equations, from what can be grasped to the ungraspable. It had to be like this, didn't it? For the questions have not and never will end while human imagination does have its limits. Let us focus again on black holes towards the end. The whole point with those is that they draw to them all information around them. How would you know anything about them then? They should be invisible, simply invisible, unimaginable, if that is a word. Yet people have predicted, discovered, and imaged them. Think about it all for a second. Mathematics is nothing less than the mightiest tool at our disposal when our imagination has reached its limits. Thanks for staying with me to the end. Join me on socials and YouTube or check out kindnessthrughnowledge.com to book a presentation. See you next time.